I think start recording. Yeah. Okay. Okay then. So welcome to this Midsem workshop, and I'm Adithya Nandakumar, and I'm currently in my fourth year, and we'll be going through the Midsem portions for the course Computer Programming, so which is our first year course. So yeah, without any further, let's start the session. So I guess people will join in as we go on. So yeah. So in terms of the content for the midsum topics, so you will be guys be having the number system. So we'll be going to the types of number systems and how do you convert from one number system to another. Then how to deal with negative numbers and then binary addition, then the floating point representation, and finally how characters are represented. Then the next we'll go into is the basic structure of C programming, and then we'll go into the data types and then what are the different operators and expressions. And we'll also go into like selection statements, so that is like your if else statements and also your switch case statements, and as well as your repetition statements, which is like your for loop, while loop, and do while loop. And finally we'll conclude with arrays, so which is one dimension and multi-dimensional arrays. So I'm not really sure if arrays has been done yet. So yeah, so I'll be like trying to give a basic idea what arrays are, and yeah, that's that. Okay, then let's start off with the number system. So they are basically like, so there are mainly four types that you have studied in your classes. So after this, the major types are basically like your decimal, binary, octal, and hexadecimal. Right? So for the respective type, like if you check for decimal, basically their weight is 10 basically. And the values that you have is starting from 0 all the way to 9. Similarly, for binary, their weight is 2. So, and then the respective digits that you can have is 0 and 1. Octal is from 0 to 7. And finally, hexadecimal is like from 0 to 50. So you can see these alphabets here, A, B, C, D, F. So basically, so as you can see here, right, because if, so after 0 to 9, so these basically, so if I consider hexadecimal, so A basically represents the number 10, and B is basically 11, C is 12, D is 13, E is 14, and F is 15. So yeah, so these are like the four nine like main types of number systems that we'll be dealing with. Now, if we're going to the next part, we'll be going into the different conversions. So how do you convert from decimal to binary, octal, and hexa? How do you convert hexadecimal, octal, and binary to decimal? And how do you convert binary to octal and decimal and vice versa? And yes, and there's also one more type, that is how can you convert hexadecimal to octal. So let's start off with the conversion. So first we'll see how to convert decimal to binary. So the first problem that we have here is this number, right? So we have 123. And the way you would be writing this is like, so we'll have this number, and to denote that it is decimal, we'll write it something like this, base 10. Now the thing is, right, so binary, we know the weight of binary is 2. So what we'll do here is we'll simply repeatedly divide this number. So if I take this and you try to divide this number, so if you're trying to divide this, basically you get as 61. Now if you do this, basically you know that the remainder for this division is going to be 1. So we'll put this number over here. So you just continuously divide this. So we can divide this with 30, which will give you a remainder as 1. 2 divided by 15 will give you 0. So if I go with 7, it will give you 14. So the remainder will be 1. 2 and 3 will basically give you the remainder as 1. Then finally 2 and 1 will give you the remainder as 1. Now once you're done with this, you can just simply take the, so whatever reminders you got, you just simply take it in this order, starting from here till here. So finally, you will basically be getting 111011. So this is your binary number for this particular decimal number. So I hope so this part is clear, right? Now the next, we'll be going to the same number, but here we have a decimal. So until now, I hope you are clear about how you can convert a normal number, like a normal whole decimal number into binary. Now the way you'll be converting this number, so there is like two parts to it. So one is the whole number, which is 123. So I'll just say will be like 123. And then you have your fraction part, which is basically your 0.50. Now this, we have to convert this into a binary. So the binary form for this, we already found out, it is basically this one, right? So now how do you convert 0.15 into, so I'll just do one thing, I'll just do this, okay, I'll just write this entire thing with blue, just to, okay. So the way you will be doing this, so you take this number 0.15, you simply multiply with this 2, with 2. If you multiply with 2, you will be getting zero point 0.3. And what we'll do is you will take this, right? So whatever whole number you're getting, you simply take that. Now next you will take as zero point 0.3. So just make sure whatever you get. So typically over here, you will either be getting 0 or 1, right? So irrespective whether you're getting 0 or 1, just make sure that you're writing the next as, so you're making this whole number as 0, and then you're multiplying. So again, you multiply this, you'll get 0.6. Again, you get another 0 here. Now again, if I do 0.6 into 2, again we'll be getting 1.2 here. So we'll be getting 1 over here. And then 0.2, if you multiply with 2, you'll be getting, I think they are making a mistake over here. Or okay, let's see here. So again, if you multiply with this here, you'll be getting zero point 0.4. So as you can see here, so once I got 1.2 over here, I made sure this is converted. I put this into 0, and then just zero point 0.2 into 2, 0.8. Okay, so over here, what? Okay, so you typically, so I'll do one thing. I'll just change this question from 1.5 to 7.5. It's just that, okay. If I go this to change to 0.75, so if I do multiply 0.75 with 2, you'll be getting 1.5. Take this. Now you put this as 0.5 into 2, which will be getting as 1.0. So over here you can, so you will stop once you get 0. And once you get 0 here, you just simply write it in this way. So if I go in this way, this is basically nothing but 0.11. So finally we'll be getting 1, 1. So what happened was, in the previous case, when I was doing it 0.15, so 0.15 was actually a number which you cannot fully represent in binary. So because of that, what would happen is that you will be doing this process for a pretty long time. Like you'll be doing this continuously. Yep. So in that case, yeah. So you will eventually get like a repeating pattern, and yeah. So whatever answer you'll be getting, basically it will be somewhat infinite. So therefore, when they do ask for these type of questions, like this type, they won't usually ask where you have to do it continuously. So again, so I hope so. This part is clear about how to convert decimal to binary. Now let's go to the next part, which is how to convert binary to decimal. So the first thing, okay, so let's take this number here. So 111 is okay. So the way you'll be converting binary to decimal is, again, we know for binary the weight is 2. So what you will do is, okay, first I'll write the number in this way. And what I will do is, for the respective digit, I'll be taking their respective weight. So so for this, if I started from over here, this is going to be 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and this will continue till 2 to the power 8. Next, what we'll do is you simply multiply with the respective values. So this will be 1 into 2 to the power 8. So 0 into 2 to the power 5 is nothing but 0. and finally 2 to the power 0 into 1. So if we do this basically, so 2 to the power is nothing but 256, so this will be 128. So it's only 16, 8, 1. So this basically then be valid here, so this will be 3. So this will be 80, 88. So finally we getting us 477. And yeah, so this is how you'll be converting binary to decimal for a whole number. Now the second part is okay. So this is the same binary, but then again I have the binary part of this. I mean the decimal part, the fraction part. So what we'll do is the fractional part is basically 0.11. So I just write it in this way. So what I will do is if this is 2 to the power 0, anything which is in the fractional part from this side will start off with 2 to the power minus 1. So with minus 1 and minus 2. So this is basically nothing but like, so 1 by 2 plus 1 by 4. So nothing but 0.5 and 0.25, which is basically 0.75. And we know like 1110 is basically the same question. So that is 477. So therefore it is going to be 477.75. So I hope so this is clear. Now, if you're clear with decimal to binary or binary to decimal, the same exact process is going to happening when you're going from decimal to like if you're going to octal and hexadecimal. So if I take this question quickly here, which is 221, again just like here for binary the weight was 2, and we know for octal it is going to be 8. So just simply divide this number repeatedly with 8. It will be 16. Yep. So the remainder will be 5 over here. Yep. So when you do this division here, so you'll be continuing doing it until you'll get a reminder which you can no longer divide with 8. So finally, again, you can, if you go in this way and like the numbers will be basically getting as 335. I think that, yep. So I hope so this is correct. Okay. Now again, the same thing over here, the next part. So we have a fractional part. So just like how we did for binary, with here, we just simply multiply with 8. So if I do multiply, this will be 0. Okay. So this is just one step over here. So finally this number, and we know like for the 10 is basically number 335 of 8. So therefore it's going to be 335.1. Okay. So this is how it will be represented in decimal. I mean in octal. Now similarly from octal to decimal, again the same thing that we did for binary to decimal. You take these numbers and then you take the respective powers of 8. So a to the power 0, a to the power 1, and a to the power 2. So this is nothing but 64 into 2 plus 8 into 4 plus 7. So this is the decimal for this. And then similarly, if you go for the next number, which is 247.3. So again, we know 247 is basically nothing but 158. I mean, this is in octal. Now, how do you take zero point 0.3? So you can again take it as 0.3. So again, if you take this as a to the power 0, from here onwards, you take this as a to the power minus 1. So which is nothing but 3 into 1 by 8. So this is finally going to be 0.375. So therefore, it's going to be 158.375. So I hope so both these processes are clear. If you have any confusion, just let me know. I'll just write this as okay. Now, similarly, let's go to the next one, that is converting decimal to hexadecimal. So we know hexadecimal is actually 16. So you'll be dividing the number with 16 if you're going from decimal to hexadecimal. So again, you can divide this with 16. So if you go with 16 to 40, you'll be getting as this, and the remainder will be 2. Okay. So okay. So again, if you go in this way, you'll be getting the value as 262 in hexa. Now similarly over here, so if I take it as this, so 642 we know in hexa we just got it as 262. Now 0.125 you simply multiply with 60. So we're getting 2.0. So if you notice over here, right, in hexadecimal and in octal, like the whole number that you can get over here can be like between the respect. So if it is for octal, it will be from 0 to 7, and for hexa, it will be always be from 0 to 50. So we got as 2. So therefore we can say, so I mean, since if I go for the next number, it is going to be 0. So we can stop here. So therefore we can say it is going to be 262.2. Right, as clearly. Okay. So that is about decimal to hexa. Now the same thing, hexa to decimal, what you can do is, again, just like how we did for the other cases. So I guess by now you should be like, I mean, you now be thorough with this thing. So again, you take this as this, and you take the respective powers. So remember, A, if you remember, is 10 actually. So 16 square is what, 256 into 10, 16 into 3 plus 9. So it's going to be 48. So this will be 2717 in decimal. I think this is supposed to be 6, my bad. I think that's so. Okay. Now same thing over here. So you know A39 in hexa is basically 2617 in decimal. Now again 0.3, let's multiply with 16. So you'll basically getting a 0. You're getting I think 4.8. So you're getting here 4. This into 16 will basically be I think yeah. So even over here as well, we'll be getting it as okay, my bad. You're actually converting from hexa to this thing. So this basically be nothing but, so if I take this as 0.3, this will be 16 raised to minus 1. So this is nothing but 1 by 16 into 3. And I believe 1 by 16 is 0.0625. So therefore, we can say this as 2617.1875. So I hope so the conversion from decimal to binary, octal, hexadecimal, and vice versa is clear. So if there are any doubts, you can let me know. I think the conversions parts are. The next we can go for is octal to binary. So actually, octal to binary is actually very easy process. So for this, you just have to remember one thing basically. So in octal we have basically what 8 digits, right? So 0, 1, 2, 3, 4, 5, 6, and 7. So just remember that like the corresponding binary values for this in 3 digits. So for 0, it is actually 000, and for this is 001, 010, 011, 100, 101, 110, and 111. So now if you take 3754, right? So if you take 3754, you just have to simply convert each of these digits into their corresponding binary values. That's it. So this is 011, 111, 101, and 100. That's it. As simple as that. And similarly, for this as well, even if you have a decimal value, you can just simply I'll just take this so point 0.5. Even if you have the decimal value, the process still remains the same. So we can take five the corresponding binary value which is 101. So actually this is going to be 011, 111, 101, 100 dot 101. So I mean, yeah, so octal to binary is actually very easy. And similarly, if I'm going for the other way around, so I just write this in one box over here. Similarly, so what I'll do is I'll take this number, and what you will do is from this side, you will be basically taking groups of three. So this is one group, two group, and three groups. I mean, a group of 3 bits. And you just simply basically, like what you say, take their corresponding octal value. So 101 basically is nothing but 5. And if I write an arrow over here, this is going to be 5, this is going to be 3, and this is going to be 7. So therefore, this is nothing but 735 in octal. Now, similarly, now over here, so I just wrote this a bit differently. So from the whole number, you'll be starting in this way. And for the fractional, you'll be starting the grouping from this direction, like from left to right. So again, from here, we'll be taking this side. And then from the right to right side, so we'll be going from this side. And you just have to add one extra zero over here just to make the group as. So finally, if you take the corresponding value, it will be 5, so it will be 52 dot. So 110 is basically 6, and yeah, and 00 basically. Also, you can write this way or 52 dots point 0.6. And if this is clear, hexadecimal is again very similar. So over here in hexadecimal, we are having numbers from 0 to 50. So only difference is instead of taking 3 bits, you're now taking 4 bits. So this will be 00, like it will be 4. So C is 12. And this is, yeah. So this A to B is basically nothing but 10. And this is 11, 12, 13, 14, and 15 basically. Okay, now if I take B, C, D, you just simply take the corresponding values over here. So B is basically what? 11, so it is going to be 1011. C is going to be 12, so 1100. And D is going to be 30. So you'll basically be getting us 1011, 1100, 1101 in binary. Similarly, over here is the same thing. So if BCD is no, then again. So if I take this as dot 93, you take the corresponding values. And 9 is 1001 and 3 is 0011. So this is going to be, yeah, yeah, so that's about hexadecimal to binary. And similarly, binary to hexadecimal, just like octal, you're basically creating groups. Now here instead of group of 3 bits, you're taking group of 4 bits. So you take as group of 4, group of 4. So over here you just have only one bit, sir. So you can just make this as group of 4. Just to just what you say, append some zeros to it, just to make it as the group of 4. And you take the corresponding values over here. So this is going to be 1. This is 13. So uh, D and D, I believe, right? Mhm. So this is going to be 1DD in hexa. Similarly, over here, similarly, just like in octal, for the whole part, we'll be taking it from right to left. Here we'll be going from left to right. So I'll just add the 0 over here. I guess over here as well as add the 0. And here as well. So this is going to be 2. This is going to be 10. So A. This is going to be 12. So C. And this is 0 basically. So 2A dot C in hexa. Okay, so I hope so binary to hexa and octal and vice versa is clear. And finally, hexadecimal to octal. So hexadecimal to octal is actually pretty easy. What you're doing is you first convert hexa to binary and then you convert this binary to octal. That's it. So it's like a pretty simple procedure here. So again, you can convert B's. So BCD in binary is basically what? So B is 11, so 1011. C is 12, 1100, and D is going to be 30. So this is basically 1011, 1100. Now you just simply convert this to octal. So again, just like how we did, you just take a group of 3 here. So let's add one more just to make it into 3 bits here. So if you see here, so starting from here, this is going to be 5. This is, did I missed one value here? Let's check if the grouping is correct. Okay, so this is not required. So 5175. Okay. So this is going to be your octal number. Okay. Yeah, so that is it about converting like from any number system. So I hope so this is clear. I'm sorry, I just muted myself. So I hope so this is clear, right? I mean the conversion number systems. Okay, now the next we'll be going into is how do you represent negative numbers, right? So there are actually three representations that we have to represent negative numbers. So we have the signed magnitude, then we have one's complement and two's complement. So the first we'll go into is the signed magnitude. So okay, so over here we have a number over here, and let's assume that you're using 8 bits to represent this number. And just note that this is actually a decimal number always, because in signed magnitude of, yeah. So in this case, it's going to be a decimal number. So you just simply convert this into binary. So if I do repeated division with 2, so this is going to be nothing but 10111. So this is 5 bits. So to make it 8 bits, I'll be adding 2 more zeros. I mean 3 more zeros. So this is nothing but. So what signed magnitude tells me is that your most significant bit, right? So I'll write as okay. So it's a most significant bit, which is your MSB. So your MSB is going to be 1 if it is a, I mean, if it is a negative number, it is going to be 0 if it is a positive number. That's all. So in my case, because it's a negative number, so in my case, this is going to be my MSB. So you just simply change this bit from 0 to 1. That's it. That's just about signed magnitude. That is as easy as it gets. So the next we have is ones complement. So the same numbers 23. So I'll do is that, okay. So 23 in decimal, the same thing. I'll just take it as 0, 0, 0, 1, 0, 1. So what ones complement tells me is that for positive number, you take it as it is. For a negative number, you take the complement. So that means change the zeros to ones and all the ones to zeros. So in this case, since it's a negative number, you simply take the complement. So in this case, you change. So this basically then becomes 1, 1, 1, 0, 1, 0, 1. I mean, zeros, okay, and then so this. That's it. So this basically represents, yeah, so that is basically how you will be getting the negative number using ones complement. Finally, in two's complement, what you're simply just doing is you would simply take the ones complement. So let us say two's complement is basically the ones complement plus 1. So we just said 23 is ones complement of 23 is basically this. So 1110 You just simply add 1 to this. Which is basically this. That's it. So this is going to be your 2's complement. So I hope so the negative number conversions is clear. Now the next part is the ranges basically. So for signed magnitude, okay, let's say assume that number of bits equal to n. So if n is a number of bits, signed magnitude has a range between so it's going to be basically between minus of 2 to the power n minus 1 minus 1 less than equal to x less than equal to 2 to the power n minus 1 minus 1. Similarly, for one's complement is the same range as it is. Two's complement is basically going to be minus of 2 to the power n minus 1 less than equal to x less than equal to 2 to the power n minus 1 minus 1. So yeah, basically this is just the ranges that you have here and for each of these. So if they are going to ask me one mark question, then yeah, they could ask from the ranges. So that is about the ranges over here. And again, you can notice that in 2's complement, you can represent just one bit extra in terms of the negative number compared to the other two. Now, among all the three negative numbers representations, we always prefer 2's. So why do we prefer 2's complement? So there are like mainly two reasons. So the first thing is the minus zero and plus zero problem. See, in one's complement and signed magnitude, what happens if I take zero, right? So again, let's take 8-bit representation. In signed magnitude, what happens is this. So negative zero is basically going to be 1000. Yeah, yeah. So you have negative zero over here if you're representing negative zero, and your positive zero is this one. And you can see both of them are actually different. Similarly, if you take one's complement, minus zero will basically be all ones, and plus zero will be all zeros. So, yeah. So you can see that for like the same for zero, you're having basically two different representations. So that is like one issue with signed magnitude and one's complement. But if you go with two's complement, what ends up happening is that so in two's complement, if you check, so if you try to get negative zero, so we know one's complement plus one of this, so you'll notice that you will be getting zero actually. Albeit you will be having a carry, but you can discard that carry. So that's the main advantage in two's complement, that for zero you only have one representation. And the second issue that we have it, this is that minus k minus of minus. So this is actually my bad plus. So what happens in signed magnitude and even in one's complement, if you try to so let's take a simple example of two. So let's take instead of taking 8 bits, I'll take 4 bits. If you try to so in signed magnitude, so if I take signed magnitude, so this is going to be 1010. If you try to add these two numbers, you will not be getting zero. Similarly, if you take one's complement, it's the same case. So this is basically 1101 plus 0010, which basically will be not be equal to zero. But if you take in two's complement, so this is going to be 01. So this you will actually be getting zero actually. Again, you will be having a carry, but you can always discard a carry. So in these two reasons, why we prefer two's complement, since it represents a negative number the best. So I hope so that negative number representation is clear. Now the next we'll be going into is binary addition. So for binary addition, just remember these four things over here. So 0 plus 0 will give you the result as 0 and carry, and 0 plus 1 will give you the result as 1 with no carry. Similar case here, and 1 plus 1 will give you the result as 0 with a carry of 1. So again, let's see that with the what you say an example over here. So let's take 50 plus 10. So again, 50 in decimals, if you try to convert this, so this is going to be 25. And similarly, if you take 10, so 10, we know it's going to be 1010. So let's try to add these two numbers now. So you got these two numbers over here. So therefore, so 4, 5, 6, 7, 8. So 0 plus 0 will be 0 only. 1 plus 1 will give you 0 with a carry of 1. This will be 1. So 1 plus 0 will be 1. 0 plus 1 will be 1. And yeah, that's it. So this will be the binary addition, and this, yeah. So that will be like the binary value of this. And I hope you'll be able to convert this into decimal number. Now similarly, 50 minus 10. So the way you can interpret 50 minus 10 is actually 50 plus minus 10. And this you just have to simply apply 2's complement to get the number. So minus 10, so if you know 10 is basically, then minus 10 is basically going to be 0, 1, and this will be the 2's complement of this. So I hope so you'll be able to calculate 2's complement. And then yeah, just simply add these two numbers down. And 50 from previous case was, yeah, this one. Oh, yeah. So if you add these, 0 and 0 will be 0, and this will be 0 with a carry. So this is going to be 0 with a carry, 1, 0. So this basically 1 and 1 will be 0, and 0 and 1 will be 1 with a carry over here, and this will be 0 with a 0. That's it. So you can discard the carry over here. So you can take, okay. So this is basically going to be 0, 0, 1, 0, 1, 0, 0, 0. Okay, so I hope so binary addition is fine. Okay, now the next we'll be going into is the floating point representation. So basically, like whenever you have any decimal number, let's say you like if you have 2.5 or 2.75, so the way in which you will be representing this in the computer is basically in this form over here. So you can see, so that so in floating point representation, you have two types over here. So we have single and we have double. Right? So single is basically 32 bits and double is going to be 64 bits, in which we'll be mostly focusing on single. And this is basically the, what you say, the representation. So we'll understand this with a problem over here. So let's take the simple problem here. So we'll take 5.125. I need to represent this in the 32-bit single precision format. So the way you will be doing this is, first step, you convert to binary. So we know 5 in binary is actually going to be 101. 0.125 you try to convert. So if you do the thing over here, so this is nothing but 0.001. So actually, this is going to be 101.001. So that is basically the first step over here, to convert this into a binary number. Now the second step that you will be doing over here is to now convert this in the form of 1 point fraction. So when you do that, what happens is, if you try to convert, so it will be basically getting in the form of 2 to the power of, let's say, m. So if you try to do that, so this number will basically be 1.01001 into 2 to the power 2. So this is my fraction. And let's say this is my m. Now, in third step, your exponent minus bias will be m. So that is basically what this is over here. Now, what is your bias over here? So remember, for 32-bit, so I'll just write it over here. Your bias is basically a constant value of 127. So you simply add m to this, so you'll get your exponent, which is nothing but 127 plus m, which is 2, 129. And again convert 129 to binary. So if you convert this into binary, so this is basically nothing but this. So I will just remove this handwork over here. So finally, once that is done, you simply, so over here, since this is a positive number, so your s value, if it is positive, it is going to be 0. If it is negative, it is going to be 1. So finally, what you can now do is you can represent in that format. So that is, you have s fraction, my bad, exponent and fraction, where this is going to be 1 bit, this is 8 bit, and this is 23. So if you finally convert this is going to be nothing but 1 and your fraction. So this is going to be this, and your fraction is basically 0, 1, 0, 0, 1. And then you just put in the remaining bits here. So this is going to be your IEEE representation. Now the next part we have is basically converting this into the other way around. So we have the IEEE representation. You have to convert this into the decimal equivalent of this. So again, let's try to split it in this form. So we'll have 1, then, so I think, okay, and then, so this is not really that element. Okay. So this is my s, this is my exponent, and this is my fraction. So we know one thing, if s is 1, it implies it is a negative number. Now my exponent is this. So this, if you convert this into your decimal number, so I'll do what, I'll just write it over here itself. So this is going to be 126. If you know exponents to be 126, then we know your m is basically exponent minus bias. So you can just substitute the values over here. Basically getting 126 minus 127, which is minus 1. Okay. So once you got all of this, yeah, we can represent in this format. So your, let's say your x will be minus 1 to the power of 1 into 1.101. So your fraction part into 2 to the power minus 1. So this is basically a negative number. And to remove this 2 to the power minus 1, this is basically going to be minus 0.1101. And then you simply convert this into a decimal number. So this is basically nothing but 0.5, 0.25, 10.125. I think this will be 0.0625. So this is going to be a decimal value for this. I hope so. This is also fine. So you know how to convert a floating point into IEEE as well as the other way around. Okay, and then finally we are coming to the last part of this part, that is the character representation. So basically, in your computers, basically we have this what do you say? So each of your character will basically be represented in a 8-bit format, and this is basically done using a code known as the ASCII code, which is the so ASCII code basically it's the short form of American Standard Code for Information Interchange. So you can see over here that in this table, right? So for each character, you will be having the each value. So after this table, you just have to simply remember the ASCII values for these three parts. That is for 0, the decimal value of this is 48 and 9 will be 57. And for 8 is going to be 65 and Z will be 90 and small a will be 97, small z will be 122. Right. So this is basically about character representation. Right. So with this, the first part is over. So that is like a huge part. Now the next we'll be entering into the C programming part. So we'll first see the basic structure of C programming. So I'm sure you guys have, like you might have seen some of a similar code snippet. So the first two lines you can see here. So this is the hashtag include. So this is a very common line you guys have seen. You might have probably be knowing this well. And this is basically the import statement for your standard input output. And then we have the second, which is basically a definition for a macro called pipe. So this part we can call this to be your preprocessor processing directive. Then comes your main body. So like your main part where you will be basically be doing all your main code stuff. So where you have your main method, I mean your main method, and also you have other functions as well. But yeah, that's the main thing. Now in C programming, there are mainly two types of data types. So one is going to be your primitive data types, which is basically nothing but your integer. So int we call it in short. We also have long. Then we also have float. We also have a decimal, and you also have char. So that is about primitive. I believe it's called decimal. Just correct me if I'm wrong here. And then you also have your some of the user defined. So in this you have something like struct, union, and yeah. So these are the main. You also have functions, and in some cases also you also have derived data types. So derived is basically your pointer and array. So these are like the three main types you have, out of which struct and pointer is something you'll be learning about later. Struct, union, air function, and pointers. Now moving on to the types of operators that you have, operators and expressions. So we have five types. So one is your arithmetic operators, then relational operators, logical, assignment, and bitwise. So let's go into arithmetic operators. So these are your, yep. So you have basically addition, subtraction, multiplication, division, and you have the new one, which is your modulo division. So what modulo division basically gives you the reminder of two numbers. And one important note to remember is this over here, which is that the modulo operator can only be applied to integer or oh yeah, so this is supposed to be known as double. My bad. So it cannot be applied to float or double. Right, so if you have something like 2.3 modulo of 5, this is basically like 5.2, this is going to be invalid. Next we come to relational operators. So this is mostly all your comparison operators. So mainly the output for this operation you typically get either 0 or 1. So 1 is basically true and 0 is basically false. Now the next has is going to be logical operators, and this is a bit important one. So in logical operators, we have your logical not, logical or, and logical and over here. And again, the same as the last case, the input is going to be 0 or 1. Okay, now let's understand short circuit. So what happens is that if you take, let's say, your OR operator. So basically this right over here. So let's take an example of, let's say, A or B. So what happens in OR operator is, as we know, in OR operator, if either one is 1, so if any one is going to be true, or 1, you give the output as 1, right? If any one is true. So what this means is, let us say if A is equal to 1, so that implies the output is going to be 1. So it doesn't check the second operand. Similarly, let us say if A is 0, then it checks B. Right? So and it will check B, and then it will see what is the value of B. If B is 0, then it will be 0. If it is 1, it will be 1. So what does this mean is, if suppose you have something like this, let's say you have 2 or 3 divided by 0. So ideally 3 divided by 0 should give an, it's what is a division by 0 error. But what happens is the output of this is actually going to be 1. Or it will be evaluated to 1. And that is because the OR operator first checks this. So this basically never gets evaluated. Now the similar case also happens with AND, where if you have something like A and B, if A is 0, it is directly going to be 0. So again, if you have something like this, again the output is going to be 0. So this will never get evaluated. Basically the second operator. So that is about short circuiting. Now the next we'll be going into is your assignment operators. So we know in C programming, like the way you will be assigning a variable. So if you have something like int x, you use something like this. Yeah, this is single equal to sign. So that is basically you're assigning this value to x over here. Now, apart of this, there are actually some shorthand representations as well. Like let's say if you want to do something like x equal to x plus 10. So this is the same as x plus assigned as 10, as you can see over here, right? So this one over here. So similarly, you basically have yeah. So whatever operators you have, you basically over have here as well. Yeah, so that is basically about assignment operators. And yeah, we're coming into the next part, that is increment and decrement. So this is another case of your, what you say, assignment operator, where if you're doing something like this, let us say you do x plus assigned as 1. So this is nothing but incrementing. So the same thing can be represented in two ways. One is your pre-increment, which is nothing but x, so v plus plus x. Another is post-increment, which is x plus plus. Similarly, x minus assigned as 1 is again your decrement. Again, we have the same case, we have pre-decrement, which is minus minus x, and post-decrement. So the difference between these two, you will be under. So what happens in pre-increment is like typical. So whenever you're evaluating anything with pre-incrementing, so okay, I'll explain this with an example. So let us say you have something like int x equal to 10. Let's say y is equal to 2. Now let's say you say something like int z is going to be plus plus x plus y plus plus. So what happens over here is, yeah, so when you do plus plus x, so this is going to be pre-incrementing. So it first increments, then take that value. So basically, if you do 10 plus 1, it will be 11. And yes, x value will be updated as 11. So x will be assigned as 11. Now for y plus plus, what happens is here as well. So what happens over here is you first take the value, then increment. So in this case, what happens is, so when you do y plus plus, since it is post incrementing, so before you increment, you'll be taking 2 first. First you take the value. Then what happens is, so yeah, so this will be x equal to 11. Then your y value still will be updated as 3. So finally what happens is z will be assigned as, so x plus plus x will be 11. So 11 plus 2, which will be 30. So this is basically how your post increment and pre increment works. Now the next part we'll be going into is the bitwise operators. So these are the operators that happens at bitwise level. So these are like your main 6 bitwise operators we have over here, which will be going into it. So first we have is bitwise and. So let us take two numbers, x equal to, let's say 10, y equal to 4. So if I do something like x equal to, so by the way, this is single ampersand. So if you do something like x ampersand y, so in binary, what happens is you're basically doing and between the two numbers. So you take as 1 0 1 0, you take as 0 1 0 0. If you're and, you're basically be applying the and operation. So 0 and 0 will be 0, 1 and 0 will be 0, this will be 0, and this will be 0. So finally, you will be getting z as 0 actually. So that is about bitwise and. Bitwise or is the same. Again, if you take the same example, right? So x equal to 10 and y equal to 4. So Z, this is again going to be the single symbol over here. So the vertical pipe symbol. So X pipe Y. So this is going to be in binary will be 1010 and 0100. So if you do an OR basically, so OR is basically plus over here. So this will be 0. So 0 or 0 will be 0, 1 or 0 will be 1, 0 or 1 will be 1, and this will be 1. So finally, you can say Z will be evaluated as 40 with 40 over here. So that is about bitwise OR. Next we're coming up is bitwise XOR. So again, if you take X as 10 and Y as 4. So what happens is, so again, this is going to be your caret symbol for XOR. So if I do the Z as X XOR Y. So what happens in XOR operator, so the way you'll be representing this, so if you do, let's say 1 XOR 1, it's going to be 0. Or you can say like, yeah, so it will be 0. 1 XOR 0 and 0 XOR 1 will be 1 respectively, and 0 XOR 0 will be 0. So if I take this 1010 and 0100, actually do what, I'll take this as 6. So if I do an XOR of this, 0 XOR 0 will be 0, 1 XOR 1 will be 0, and this will be 1 1. So finally you can say Z will be assigned as 12 actually. And finally we are coming into the bitwise NOT operator. So this is represented as this. So if you take x as 10, so yeah, and let's say you take y as complement of this. So you take 1010, and you're basically taking the complement of this. So this basically changes all the zeros to 1 and all the ones to zeros. So if you complement this, it basically becomes, so you can say y will be 5 over here. Okay, so that is basically about the bitwise NOT operator. Next, we'll come into the left shift operator. So this is basically this symbol over here. So the left symbol. And what basically left shift does is it basically shifts your, so typically the, yeah, so we represent as x left shift n. So it shifts the bits towards left by n. So if you take an example of, let's say, x equal to 2, or let's say x equal to 3. So in this is going to be 110. So let's say you have like some zeros over here. If you do something like y equal to x left shift 2, you'll be basically moving these bits by 2 times. So that means what happens is in first move, so if you move these bits in 2 times, it'll be 000. You get 110 and 0. So this has moved twice. And this is basically 12. Right? So that implies y is 12. And one more thing is basically x left shift n is basically the same as x into 2 to the power n. So this is, yeah, so this is like another way to think of a left shift as basically. Or we can also say that, so if this is the case, we can directly say one left shift n is basically the way you can calculate power of 2. So that is about left shift. Right shift is basically the opposite. So rather than going for the left side, we're going to the right side basically. And the symbol is x right shift n. So the same thing as the previous case. So if you take x equal to 3 over here, or let's say you take it as, so if I take the opposite of this, let's say 12, y will be x, let's say the right shifted by 2. So what happens is, let's say you have few zeros here and you have 1100. So this will be right shifted by twice. So this would go twice on the other side. So, so if you go over here, so 1, 2, you basically moved it twice over here. So, so finally we can say your y will be 3. And you can also say that just like the previous case, x right shift n is basically the same as x times, let's say, x divided by 2 to the power n. So yeah, that's about a right shift operator. And yeah, so that marks the end of all the operators we have discussed here. So this is what we call as the operator precedence. So according, so you can have we can have like expression questions where which will be like based on this operator precedence. So if you see here briefly, we can see that the first we have is a parenthesis operator over here. So this has the higher precedence. And then these are the two operators that we'll be learning about it later on. These are basically related to pointers. So we might discussing anything about it. And if you see over here, this is like your increment operator, decrement operator. And this is going to be your, yeah, and this is going to be a complement operator. This is going to be, yep. So we have a star here. You have your ampersand size of entire. So over here, if you see, we have like two stars over here. So this star is basically like your multiplication one. And this is basically more of a dereference symbol, which you'll be learning about it later. So you don't need to worry about it as of now. And this is basically a bitwise operator. And yeah, basically all these are like your, operators that you can have here. Okay, so let us see one problem over here. So you have A as 10, B as 5, and C as 5, and they're telling you what is the value of this. So again, it's a pretty simple problem. So you take 10, A is 10, equal to B, if you substitute B 5 plus 5, which is nothing but 10 equal to 10. And because 10 is double equal to 10, this will be evaluated to 1. So therefore your D will be assigned as 1. So when you print this, you'll basically be getting the output as 1. That's about the first part over here. Now the second part, there are like a bit of things that is happening here. It's an MCQ question. Okay, so you're taking I as 10, J as 4, D as 3, X is minus 1.5, Y is 0.5, and C is 5. Okay. So now you're having some expression over here. So first is plus plus x. So what happens is you're doing a pre-increment operation. So you'll take minus 1.5, but just remember x will be changed to, so it will be incremented, so it will be minus 0.5. Next, you're multiplying this with, again, another thing, that is your your pre-increment of d. So this is going to be 2. Oh, my bad, this will be taken as 0.5 over here since it's pre-incrementing. So for here also it will be 2. So again your d will be updated to 2, and you're dividing this with y plus plus. So that is going to be a post increment operator, which is, in this case, will take zero point 0.5, but your y will be updated as 1.5. Now, if you do evaluate this, you'll see that okay, c will be minus 0.5 times 2 divided by zero point 0.5. So you have to apply the operator precedence. So you'll first be evaluating this side, since multiplication division has the same precedence. So you'll go from left to right, and then you finally divide this with this. So this is nothing but basically minus 1, and minus 1 divided by zero point 0.5 will be minus 2. So we'll be getting C as minus 2. Now we are taking x. X is my pre-increment of y plus 1. So I just write this part over here. Your x is going to be minus, so this basically entire part is this. It's basically nothing but, so again, if you check the updated value, so y was 1.5, so now you're decrementing, you're performing a pre-increment. So this basically then becomes 0.5, and your y value becomes 0.5 only, and you're doing plus d, so d will be 3. So finally it's going to be 3.5, and you're basically printing c and x. So therefore your output basically is going to be minus 2 and 3.5. I think I made a typo over here somewhere. Okay, my bad, d is 2 here, my bad. So it's 2.5. Yep, so it should be this here. Okay, so I hope so I'm correct over here. Let's see. Yep, so I think this is the same as the previous one over here. Okay, so I'll just check that. And these are two problems related with the bitwise operator. So first, let's check with A is 4, B is 2. So when you take x equal to, so this 4 left shift 2 plus 1. So you have a precedence first over this operator. So this is nothing but 4 into basically 2 to the power 2. So that is 4 for 16. So you'll be basically getting 16 plus 1, which is 17. Similarly, over here, x is going to be, you'll be putting the respective values. If A is 7, B is 3, and C is 2, it is going to be 7 plus 3, left shift 2, and A or B, I mean X or B. So X or in this case will be 7, X or B. That will be 2. So over here, we first giving precedence over, so we can refer to the operator precedence table. And you can see, yeah, so you're giving the first precedence over to this guy. Then you'll be having the over this, and finally over this. So this is basically going to be x equal to 7 plus. So 3 left shift 2 is basically nothing but 3 into 2 to the power 2. So this is going to be 4, that will be nothing but 12. And 12, if we do it quickly over here, so and of this is basically 1011 and 101. So this is this, and finally 1101 XOR of 0011. That's going to be 0111. So this is basically nothing but 14. So therefore x is 7 plus 14, which is nothing but 21. So that is basically, so that is about summarizes all the operators here. Now the next we'll be going into is typecasting. So there are two types of typecasting. One is basically implicit and other one is explicit. So when you talk about implicit typecasting, what happens is, let's take int x is assigned as 2, and let's take, let's say, float y is equal to 3.0 and z is 2.5. So now when you're trying to do the addition, let's say float a, let's say x times y plus z. So what happens over here? So first x will be converted to float. So first we'll have it as 2. This is basically int 3.0, which is float, and then we have z over here, which is 2.5, which is again a float. So the thing is, what happens is the mesh. So the compiler automatically will try to convert whatever shorter sized value we have into like a more larger value. So in this case, this int value basically converted into 2.0, which is the float, and yeah, so we'll lose the remaining operation here. So this will be 6, 8.5, and this 8.5 will be stored into a. So you can see that in this case, the 2 got implicitly converted into float. And now the next, we also have something known as explicit typecasting, where you're basically mentioning the type. So if I take, let's say, int x equal to 2, so if, yep, so you take int x equal to 2. Let's say you take float, y will be, let's say, 2 divided by, so the way, so if you want to, let's say, convert 2 to, let's say, float, you can mention like this. So float over here, x divided by 2. So what would happen in this case is x will be implicitly converted into float. So this basically is equal to 2.0. So this basically becomes 1.0, and that will be assigned. So that is basically about two types of typecasting over here. Now the next, we are now entering to the next part now, which is nothing but the selection statements. So under selection statements, we have if block. So the syntax for if block is basically you have your if and then your expression. So your whatever is a condition expression, and then you have basically whatever body you have over here. So that is basically about your if expression over here. And similarly, you have your if else block, which is again similar case, and otherwise else. And finally over here as well. So the syntax for this is you have an expression over here, and then you'll basically be having, okay, so that is one body here, and then you have else if, another expression, else. So you can have as many number of else's by if you want here. Okay, so that is about the conditional statements. Let's see one problem related to this. So okay, so we over here we have hi equal to 1 and hello equal to 0. So you have a if condition here. So this is an expression that we have over here. Let's say hi greater than equal to 1. So we'll check this, or so plus plus hello. Okay, so the first thing, if you see over here, 1 greater than equal to 0 is false. So because this is false, the or operator will go to the second part now. That is going to be plus plus hello. Now again, plus plus hello will be taken as 1, and 1 is not greater than 4. So ultimately, this entire expression will be evaluated as 0. So as a result, what will happen is your output is going to be empty in this case. Yep, so that is basically about if else statement. Next, we are entering. Now the next we have over here is the switch case blocks basically. So the way this looks like this, we have a switch in which you have a variable, and then you have a case in which you have an expression over here. and then some statements. So you can have as many number of case statements you have, and finally you have default. So, so what basic does is that it will try to match this variable with the expression, and if it can't find any match, it will then basically executes whatever is in the default block, basically. Right. So now the next part is basically using the break statement. So, so what happens over here is in switch statement. What happens? So, if let's say take a simple example, let's suppose if x is equal to one, and let's say you're switching it with one. Let's say we take a simple example. Let's say case one, print f hello. Otherwise, let's say case two and default. So what happens over here is if I don't have a break statement over here, so what end up happening is okay. So it will check okay with this expression. You can see it has a match. So it will print hello. So this particular statement over here will print hello. But now because there is no any break statement, it will also execute the ones below as well. So you're basically getting hello, world, and bye. Therefore, it is important that you need to make sure to include a break statement. So if I try to do this, so by including a break statement in here, you can ensure that only one of the cases is executed. So it will basically be printing hello only. So that is about the case block, like the switch case statements. Now next, let us look into one problem over related to this. So yeah. So over here you have a macro size which is defined as 20, and then you have calculate this value, and you're doing a switch statement over here. So let's see this first case over here, which is size. So size is nothing but 20. So this is basically nothing but 0. So this is going to be not considered. Second, we can have a case, let's say size minus 2 times. So size is nothing but 20 minus 2 times 5, which is nothing but 10. But again, it's 5, so it is not 10. So this is not equal to 5, not equal to 5. Next, we have is default statement. So that's we are not taking that. We'll check the next case, that is case size over here. So size divided by, so that is 20 divided by 2 times 10. So 20 divided by 2 is nothing but 10. And 10 divided by 10 is 100. This is also not equal to 5. And finally, another case, let us say this is going to be size minus. So 10 minus 10 divided by 2. So this will be validated first account to operator precedent. So this will be 10 minus 5 will be 5. No, my bad, 20 minus 5. Huh? So this will be 50. So this is also not equal to 5. So therefore, it goes to the default statement. Now, if you see in the default statement, it first prints XL. So first prints XSL. But now what happens is because there is no break statement, it therefore executes the remaining ones basically, whatever ones is below this. So you'll be getting XSL, L, and M as well. So finally, your output is going to be this one, option C. Right, so that is about that. Now the next let's look into is this one over here. So if 100, print high or and print hello, else print welcome and print bye. So first thing is 100. So 100 basically, if you are just writing a constant value, so one thing you can notice that if basically if you're writing a constant value, so if this is not a, what do you say, evaluated to zero, so if this is, what do you say, 0, 0.0, or an empty character, all of this is basically evaluated as 0 only, and the rest all will be 1. So therefore this is basically true. So therefore what happens is it prints hi and hello. So therefore we can see there will be an hi and then there will be a hello. Now one thing you can see is this is an else block without a curly braces. So when you have an else block without curly braces, it is only a one statement block. So this is what will be considered in the else statement. So this is basically the else block. So the remaining you have is print by. So that will also write as print by. So this is going to be your output. So that is about your selection statements. Next, we'll go into the repetition statements in which you have a while block. So the way it looks like this, you will have basically a while and an expression, and then you have some body here basically. So as an example, let us say you take int I equal to 0, and then you have while I less than 5. So in this case, you will say printf and then I plus plus. So over here, it is important that you need to have some sort of an update block. So this will be like your initialization of the loop variable. So what I mean by loop variable, so this is basically any variable that is affecting the expression over here. So the main issue is if you don't have this, will basically lead to an infinite loop. So no update of loop variable can lead to an infinite variable. I mean infinite loop. So that is about the while block over here. Now next we have is a do while block. So what happens? So this is how basically a do while block looks like with an expression. And what happens? The main difference between this and the while block is that this will execute at least once, or it will run at least once. So even if you have something like this, let's say, imagine you have in IS5. So you can see that in this statement, if you see, although the condition is false, because this is a do while loop, it will first check into the body of the letter before it looks at the condition. So therefore, your output is still going to be hello. So that is briefly about do while block. And finally, we'll enter into the for block basically. So if you go into the for block, so the way it looks like is we have a for loop in which you have initialization. Then you have a semicolon. So after initialization, you have a, I'm sorry. So for initialization, after initialization, you have the expression. And finally, you have the update block. So then you have a body over here. So as an example over here, you can have something like this. So we have for int I as 0, I less than 5, and I plus plus. And then you have, let's say, printf I. So this is how a for loop looks like. So one small thing to consider is that all these blocks are actually are optional, by the way. So that means here initialization, expression, and your update, all of them are basically going to be optional. So what does that mean is you can have something like this as well. So you don't have an initialization block, but you have a condition, let's say I less than 5 and I plus plus. Or you can also have something like this as well, an empty for loop. And this is basically going to be an infinite loop basically. Why? Because by default, your expression is going to be taken as 1. So that is about the for block. And next we come into break and continue. Yeah, so basically what break does is it abruptly stops the loop. Meanwhile, your continue block, basically it skips. So if you take something like this, and if you say if I is equal to 3, you break. So this basically will output of 0, 1 and 2. So the moment it reaches 3, it basically stops. And similarly over here, if you do the same block, so I'll just copy this entire thing. So instead of break, if you have continue, it will skip 3, but it will print 4. So that is basically the main difference between break and continue. So that is, and again, another thing as well. Okay, so let us see a few problems related to this. So the first one that we have over here is okay. So we have n as minus 10, and then we are saying okay, while n is less than minus than 2. Okay, so we'll first increment n. So what happens is now n becomes minus 9. So from minus 10 we give to minus 9, and if it is equal to minus 4 or equal to minus 10, we'll skip. If it is equal to minus 5, we'll print quiz. Else if it is equal to minus 2, we'll break. So basically we'll be going all the way up to minus 2. So in this case, we'll be printing minus 9. So minus 9 will be printed. Next of what happens, it gets incremented. So from here it becomes minus 8. Again, minus 8 will be printed. Minus 7. So what happens is minus 7 means you'll be skipping this. So it'll be continue. So nothing will happen. So you get minus 6 will be, then you print, then you go to minus 5. So at minus 5, what happens is you will be printing quiz. And after that is done, you'll come over here and you'll printing minus 5 again. Next, we'll go to minus 4. Again, it skips. Minus will be printed. And finally, minus 2, it will stop the loop. So finally, the output is going to be this. So that should be this one over here. Yeah, so now right over here, there's an interesting thing over here. So x is 5, y is 2, and c is 2. So we have something over here. Like we have x less than equal to 5, comma, y less than 3, comma, c. So this basically over here is a comma operator. So basically what comma operator does is basically like the last one, the last element is taken. So it basically evaluates to the last element. Right. So in this case, will basically be evaluated to C. So ultimately this can be reduced into while C. And while C is basically nothing but it's an infinite loop. So therefore it will be over here. Okay. So that is about this part over here. So up until here, I believe this might have been covered in classes. So the next part we're going into here is arrays. So the way you'll be declaring an array in C programming is there like a few ways of declaring. So one way you can declare it as something like this. So you have a data type, right? And then you will have a variable. and then something like this. So you can either you can have a size, and this way you can have it. So you can have something like int a10. Second way, you can also declare it in this way. I'll just copy this thing. So you can have a size here, and you can have an element over here. So you can have something like int a of 5 equal to, let's say, 1 and 2. So this basically be 1 and 2, and the remaining three elements will be 0. Will be filled as 0. One more way in which you can do is, you don't need to mention the size, but you need to mention the elements. So it will look something like this. So that is about the array, like the different ways you can declare arrays. Now, how do we read? So now, once we know about this, so commonly, like in the questions, they do ask you to, like, make sure that the arrays that you're creating is read from the user. So let's see how you can, create an array by reading an input from a user. So the first thing that you always need to have is the size of the array. We need to know what is the size of the element of the array. So we'll first ask from the user the size, basically. So by getting the size, okay, so we'll first ask the user for the size of the element. So you can say size, and then you can just store this in this. Now, once you know the size, you can just simply make a for loop, and this is how you will be always be accessing an array. So 0 I less than size. Let's say you can say printf enter element, and then you can say okay. You can just scan of this in your array. So before that, I think I just have to make sure I just write that. And this is how you would be reading an array from a. So let's just put this here, and let's say. So this is how you'd be reading an array from a user. Now, how do we be printing an array from a user? Again, you can just simply use the for loop block over here. So I just so you can just say printf of I. So this is how you can simply print a array. Right. So that is basically how you can print an array. And yeah, so now the next we'll be looking is, if you know how to, again, if you know how to, like, what you say, access an array, you can easily be able to do this one, which is to get the sum of an array. So let us imagine that you have an array of size 5, which is 1, 2, 3, 4, and 5. So the way you will be doing this is simple. You just simply declare an sum variable which is 0, and then you simply, iterate array. So you can just simply iterate through the array. So this will go all the way to, let's say, is 5, and you simply add in the sum and finally print. That's it. So that is how you can easily get the sum of an array. Now next is, in an array, how you can get what do you say, the max of an array as well as the second max. So here the idea what you can do is you can just initialize int max as some low number, let's say minus 1000. Somewhere let's say max 2 will also be 1 less 1000. So again here the idea what you can do is you can just simply write a loop which will go all the way to size. So you'll be checking few things. The first thing is if this number is greater than your max, then you then check whether the max is what do you say greater than max 2. In that case you will take max 2 as max, and then you can just simply say okay max will be assigned as this. Else if you will check if max 2, if this array is happens to be greater than max 2, in which case you just say max 2 will be assigned as array. Yeah, and that's it about this part, how to get the second method. And then we have finally the last part of this thing, which is nothing but the multi-dimensional arrays. So a multi-dimensional arrays, if you check how can you declare a multi-dimensional array. So you will have your data type, then your variable name, and because this is a 2D array, so up until now what we have discussed is one dimensional array. So in 2D array you will basically be having like it's basically nested array. So the first will indicate like the number of outer arrays and second will be your inner array, or you can think of this as like the number of rows and columns. So you can take it as R and C. So the example could be something like int matrix of size 2 and 3. So this is where you typically declare an array. And the way you can be printing it is basically, in this case, since it's a nested loop, you will be having two loops here. So let us assume we have I rows, let's say R rows, and so I'll either call it as N rows and M columns. So in this case, we can have two loops here. So for int I as 0, I less than N, and I plus plus. So and then in this way, you will be accessing your 2D array. So in this case, you will be having your you'll be using two. So the first will be to get the array and second to get the element. And yeah, that's it. So this is how you will be printing 2D arrays. And yeah, so with this, we'll come to the end of the session over here. And you guys have any doubts or anything?